recite half of my CV, but that's very kind of you. I've actually been very minimalistic in my presentation in the sense that I haven't prepared myself, so I hope you will forgive me for that. I don't have any slides, and I'm just going to revert back to writing things on the board. It's probably an appropriate style for a subject like this, given that I'm in the middle of thinking about these ideas, and I think it helps me probably clarify some of these things by going at a slower pace. What I want to really talk about is the nature of correlations in quantum mechanics, and there is a kind of a new development in this area, which is in addition to it's either entangled or it's not entangled. That's kind of the conventional view, and now we're starting to realize that there may be an extra type of correlation there, which may be useful in the sense of even contributing to efficiency when entanglement is absent. And I think last time I spoke about this, someone actually said, what you are telling us now is very revolutionary. So I want to make sure that you understand that what I'm saying now is not revolutionary at all, and I'm not going to say anything new actually that's not known. It's really just going to be a summary of things that we worked on and are doing currently. So basically the idea of correlations is really somehow in the early days of quantum computing, people said that entanglement was really the feature that was responsible for everything. So if you didn't have entanglement in your system, you would never be able to get anything that's significantly more efficient than classical information processing. But now this is challenged a little bit, and in fact you even have people who claim that maybe you can get exactly the same efficiency without any entanglement and so on. So there is a question then of, what's the useful resource? Can we identify anything like that and so on? So I'll give you a rough idea of this. It will help probably if we speak about bipartite systems, simply because you can see how some of these ideas enter there. But I think most of what I have to say applies to any dimensionality and any number of subsystems. So it's very general. So let me tell you about correlations as we understand them now. So by definition, and again this definition emerged from various kind of protocols. So again, all of these things are defined in some kind of pragmatic physicist sense of that word. What we know is that when you talk about bipartite systems, so you take some state with subsystems A and B, traditionally what we want to know is whether this state can be written as a convex sum of product states. And this is what we call a separable state. So basically this could be any general state of two subsystems. And then what we talk about is states that can be written in a way like that. Basically a probability distribution. This could also be continuous if you like. And here is a density matrix for A and another one for B. And again, this state emerged from one of the papers of a guy called Reinhard Werner, who in fact had these guys in mind when it came to Bell's inequalities. And he said, if you have a state of this type, then it clearly shouldn't be violating Bell's inequalities, because what you're doing is you're giving me a local description of A, you're giving me a local description of B, and all you're doing on top of it is mixing them classically. So a state of this type is like a local hidden variable theory. I mean, after all, quantum mechanics at this level, if you confine yourself to these states, is a good example of a hidden variable theory. And therefore, he took this as a definition of something that's in a way classical. It doesn't contain any quantum correlations. And this is something that lots of people have analyzed, and there are many ways in which we now try to quantify these things. And I will tell you a little bit about that, because that's part of the general picture that's now evolving, and I want to tell you about it because it's something I'm doing at the moment, and it's interesting to me. But now, the novel addition to the whole thing, and I think it came about from two directions, and I will tell you about both of them. Is that basically a subset of these guys is effectively what you would call a classically correlated state. So there's a little bit of a kind of diversity in terms of language that we use, and I think some of this may be confusing. So lots of us would call this only a classically correlated state because it's not entangled, if you like. But what now people are starting to call classically correlated states are simply states where you have an orthogonal basis for A and another orthogonal basis for B, and also mixed with some probability. So what I want to say is that if you give me something like Qij, and you have some projector for A, and you have some other projection for B, then what this is some kind of description where I have, so the key thing is that these guys are orthogonal to each other. So I have an orthogonal basis here, another orthogonal basis here, and so let me just give you an example rather than write it highly mathematically all the time. If you had two qubits and basically both of them were either in a state 0 or 1, this would be one of those classically correlated states. So in a sense, you can say Alice has a basis 0 and 1, Bob has the same basis here, 0 and 1, and whenever Alice has a state 0, so does Bob, and the same for 1. So this is a state that really is the same as if you had two random variables that were correlated to each other. And in a way, you really would not expect this guy to do anything better than a random stochastic classical computer. That's the point. So if you really show me that your computer is always in a state like this throughout the computation, then of course you can simulate this classically by definition. Okay, so that's where the logic comes in. And then, why could this be any different? Well, because you don't have to have an orthogonal basis in which to expand a state like this. So let me give you an example of a state that belongs here but doesn't belong there. And it's very simple. It's the same as that guy, provided that I rotate one of these ones into plus, for example. So state plus is nothing but 0 plus 1 state. So here you see I've got an orthogonal basis on Alice's side, but on Bob's side I'm using two non-orthogonal states, so they are not fully distinguishable, and in that sense they are not classical states. I'm using the superposition principle, whereas here I'm not using any superposition principle. I'm always in the same basis. And I think this somehow is a state which does have extra quantumness on top of this. And the question now is, would you expect this kind of state to be better at doing certain type of information processing than the fully entangled state? And that's actually what quite a lot of people are thinking about now. So somehow you have a fully entangled state. If you destroy entanglement, you will get one of those separable states. If you destroy even superpositions locally, then you will get a classically correlated state. That's the terminology now. So entangled, separable, classically correlated. And then the lowest of the low, if you like, is state that has no correlations whatsoever. Okay? And the question is now, can we first of all understand this structure? Can we quantify each of these gaps, if you like, and say how much entanglement is there, how much people call this discord. So that's going to be the word that we'll be using more and more. And then how much classical correlations would there be in a typical quantum state. And you can see that you can add as many subsystems as you like and repeat exactly the same story. It extends in exactly the same way. There's no loss of generality. So now, why are these guys thought to be more exciting than just classically correlated states? And the reason is that we have one or two examples where it seems that the speed up is still a significant speed up. There's an exponential speed up, even though there is no entanglement present in the quantum computer there. And that's actually one example I want to present for you now. It is a little bit of an artificial example, but then quite a lot of quantum computation is a little bit artificial to show the difference. So we don't, if I don't have anything mind-blowing to show you, to convince you that this is really exciting. So the algorithms go under the name of single pure, although even this is not going to be quite true actually. Even this single pure qubit is not going to be pure. but let's call it single pure qubit algorithms. It's a kind of class on its own, and as a computer scientist, which may be interesting to you, you can study the power of this class, and you can say how different this is to allowing all the qubits to be pure and so on, and how different it is if all the qubits are mixed to a certain degree. So it's a class that actually is more powerful than just a classical computer, and that's going to be the key to what I have to say, because clearly the states are not going to be describable in this classical way, and yet I can show you that they're not entangled either. And that's where the surprise is. That somehow these guys on their own are maybe good enough for some kind of information processing. So I just want to summarize it, because then what I want to really do in the second part of the talk is go and show you a little bit how we quantify these things using information theory and so on. So there's a lot of interesting stuff. So this single pure qubit is, the game is really to have it's really an interferometer. I'm really going to do it in a fully quantum computational picture. So basically, you have one single qubit which enters as usual in the state 0, and then undergoes a Hadamard rotation to make an equal superposition of 0 and 1 here. And then something is going to happen in the middle as usual. So this is your first Fourier transform, then your second Fourier transform, and then you measure at the end of the whole thing. So the question is, what's going to be the computation in the middle? And the interesting thing is that what you can do is you can put a bunch of qubits here, and the key now will be that all of these qubits are maximally mixed, and that's going to be the surprising element. So I'm only going to allow this guy to be in a pure state initially, and I can control that. The rest of it I really don't care about at all. So each of these qubits, if you like, each of them is in a maximally mixed state, and there is n of them there. So somehow they enter this interferometer, but the way they enter the interferometer is through a conditional unitary transformation. And the key is that you will take some kind of non-trivial unitary transformation here. So they come out of this, and you don't even care what happens to them. You don't need to measure them. They are already maximally mixed, so nothing exciting is going to happen to this bunch of guys. So the whole trick is what kind of information can you infer by measuring just a single pure qubit. So it looks typically like an interferometer, and part of the, I don't think I will get to that, but I think with Brandon and a few other people from materials here, I think there's a huge interest in interferometry in general, because the way you measure physical quantities in quantum physics is by encoding them into the phase between two different orthogonal states in a superposition like this. So actually what I'm presenting here is more or less how we measure anything in physics. Any field would be measured as a kind of phase that's introduced by some kind of interaction of this type. So even though it looks like I'm presenting a very specific algorithm, and here I am, you can actually map this to many other exciting questions. Metrology, I guess, is the name. How do I determine the phase of my system? Anyhow, for the sake of this algorithm, what you need to know is that there is a quantity which describes exactly the interference that you will observe at this end. So basically the probability, now here you're talking about a probability to observe 0 and the probability to observe 1. There's only a single qubit out there. And this probability is a function, so I'm not going to go into details, it's a very simple calculation. You really only have to apply these 3 gates and then make a measurement in the 0-1 basis. And what you will see, interestingly enough, is that if you call this state here rho, that the interference or the probabilities here depend on the quantity trace of u times rho. Okay? So if you like the modulus of this guy tells you about the difference between these two probabilities, which is what you would call a visibility as a physicist. And the phase of this guy, this is a complex number in general. The phase of this guy tells you about the shift of the interference fringes when you observe them. Okay, so they're directly observable physically from just measuring zeros and ones, if you like, at the end of the whole Now, this quantity is what you can compute by making measurements here. Actually, you can show that you can compute it with a polynomial effort. So what I mean by that is that the number of times you have to repeat these measurements is really on the order of n to get a pretty good estimate of the trace of u times rho. And the punchline of this is that the rho that you're inputting is a maximally mixed state. So what this kind of interferometer does for you for free is computes the trace of a unitary transformation. Okay? So when this was first introduced by two people, Neal and Laflamme, they solved it in the following way. They said, if I have n qubits and you give me a typical unitary transformation, what you're talking about is 2 to the n by 2 to the n matrix. Okay? Imagine I give you this matrix on a piece of paper and I ask you to compute the trace of this matrix. What you would have to do is sum up the diagonal elements, but there are 2 to the n elements there. You'd have to make 2 to the n simple additions. So additions are simple, but there's 2 to the n. Here, I'm claiming that you can estimate this just after n repetitions of this kind of interference pattern. So in a sense, the way they solved it, and this is a PRL maybe 10 years old, is here is a very simple task. I mean, I don't know if you care about computing trace over unitary matrix, and yes, some people have applied it to knot theory and computing all sorts of polynomials there. It's still not very exciting to a physicist, I must admit. I think if you can map this to some kind of metrology, I'm sorry to be like, I mean, it's just a question of interest. I'm not saying this is not cool and it's not interesting to someone else. It's just not interesting to me, personally. But I think if you can really translate it into a more general phase estimation, and then say, you can do the same thing with a state like that, that would be hugely exciting to us. Okay, so what's the punchline as far as, going back to correlations and so on? The punchline is that recently, maybe within the last 2 or 3 years, the group of Carlton Caves in New Mexico looked at this. And then they said, what happens if we actually make this guy non-pure? What happens if we really depolarize it? So instead of having 0 as the input, make it something like probability 0 and some other, of course, probability for 1, and make this p very close to a half. Make it just an epsilon away from one half. So this could be like 1 plus epsilon over 2, and this is then 1 minus epsilon. Okay? But fix your epsilon, make it independent of that. What they then go on to show is that you still get an exponential increase in speed, simply because if your epsilon is fixed, what this means is you've got to repeat your algorithm something like 1 over epsilon times. There's an overhead. You have to just repeat it because you're not sure whether you have 0 or 1, but it's a constant number of repetitions. But actually you can make your epsilon so small that you guarantee that there is no entanglement here in the whole network, in the whole structure. And that somehow is surprising. So now I can make it so mixed, the whole thing. It's just an epsilon away from identity now, in some sense. But it still contains enough quantumness, and that's the question, what kind of quantumness does this contain, to give an exponentially more efficient quantum algorithm. And actually the group of caves that I mentioned went on, that's another PRL, I think 2 years old maybe, went on to say, clearly we eliminated entanglement, and we know that the state is not of this type, because otherwise this would be just the same, as bad as a classical computer there. So basically the only thing that we can actually now calculate is the difference between these two. So the states must be of this type, that they have some kind of superpositions, but these superpositions are not correlated enough to give you any entanglement. And I think there are plots in that paper where they say if you plot the discord of this state and you show how the discord scales with this, and you will see the similar kind of pattern to the efficiency. And I think that was the main point of that. So somehow from this work it emerges that these kind of correlations may also be somehow useful to us. And the question is, can we really quantify this properly, and how do we understand this? Feel free to interrupt me at any stage, by the way. So far it's clear. Very good. So now here is how this Discord came about. In fact, this takes me back to the last time I was here in Oxford, and the idea was really to try to come up with a nice way of looking at all the correlations in a given quantum state. And basically, mutual information is something that people traditionally use for this purpose. So you look at, if you like, mutual information of any state, and would be in quantum mechanics given as entropy of the subsystems and then minus the total entropy. And now at some stage, I think the question arose whether we can decompose this. I think the person actually who should really be credited for this is a guy called Lindblad. The same Lindblad as in the master equation. It's just that he wrote his papers in the early 70s, and I think by the early 90s everyone kind of forgot about what they were all about. And I'm very lucky in that respect that I get credited alongside Zurek for Discord and stuff like that, but it's really actually all from Lindblad's ideas. And the idea is the following. Can you somehow decompose this as entanglement in state rho AB and some kind of classical correlations in AB? So would you be able to write down total correlations, and are they additive? Is it even a meaningful thing to ask for? To say, well, you know, there are correlations that you can actually reproduce by classical means, whatever you mean by classical in this case, and then the rest of it is somehow entanglement. And this was in fact Lindblad's point that he made. And the point that he noticed is the following: it's possible to have, well, a maximally entangled state is an example of that. It's possible to have quantum correlations to such a degree that your reduced entropy is a maximum, but your total entropy is zero. So here, of course, we're talking about a pure state, and each of these is one unit, if you like, of entropy, but the total state is a pure state and has no entropy. And the interesting thing is that the mutual information of this guy is basically 2 bits. And Lindblad said, how come it's 2 bits when you have 2 classical bits of information, they cannot exceed 1 bit of correlations. This looks like, you know, things can be correlated to 100% degree, but this looks like 200% degree. And that's a little bit of a surprise. So classically, if you have 2 random variables, I think most of you know this, I'm probably just walking you through something very, very simple. If you have x and y random variables, and you're talking about some joint probability, if you like, for x and y, and now you have to give me, you know, 0, 0, 0, 1, 1, 0, and 1, 1 numbers, and let's say they're correlated in the same way as what I described there. 1/2 for 0, 0, 1/2 for 1, 1, and 0 otherwise. Okay. So whenever x is 0, so is y, and whenever x is 1, so is y. This guy has 1 unit of mutual information, and the reason being is that the joint state is also mixed to 1 bit of entropy. Okay? So classically, you cannot have systems correlated without the whole thing being in a mixed state. It just cannot be done. Whereas quantumly, you actually have a state that does twice as well as this. So somehow, the mutual information, if you calculate it between x and y, is here only 1 bit. And of course, this is the whole surprising thing about entanglement. So the question that Lindblad somehow said, and there is just one sentence in his paper saying, well, of course it's twice as big, because it's not just classically correlated, it's also quantum correlated. But I think he didn't really go on to elaborate on how you would quantify things like that. So now there are 2 ways of doing that, and I'll show you what I did some time ago, and then I'll tell you what Zurek did actually. Olivier and Zurek, I think, wrote another paper in which they arrived at a very similar conclusion, but through a different logic, actually. So what I try to look at is basically, if you think about classical correlations in a state, rather than looking at this kind of quantity, what you should really try to do is you should try to quantify how much you can reduce the uncertainty about the other subsystem by measuring the first subsystem. And that's the usual notion notion of correlations. If I look at, imagine you share this state between Alice and Bob. And imagine that Alice makes no measurement on her subsystem. That means that she has a certain amount of uncertainty about the state of Bob's system, which is the usual von Neumann entropy, if you like, of the reduced density matrix of Bob. But now imagine allowing Alice to make a measurement and get a sequence of outcomes. What this would imply is that Bob's density matrix would now exist in different states, depending on Alice's measurement. So Alice makes some measurement with some outcomes, AI, doesn't matter what they are, and collapses, if you like, Bob's state to state rho pi, with some probability pi. And if you ask yourself, what is the best she can do in terms of minimizing the uncertainty on Bob's side, the best she can do is some kind of average of these uncertainties. Because she knows whenever she gets outcome A1, she knows the state of Bob's system is rho B1, then A2, rho B2, and so on. So you get a quantity that's actually also a mutual information, but now defined in a different way. Defined as how much you can reduce uncertainty between two subsystems. Okay? And if you look at this guy, this is a direct analog of classical mutual information as well. If you look at this guy, of course, by definition, you cannot exceed 1 bit if you're talking about qubits here. Because this guy is always a positive number, and this is your entropy of the reduction. So in a way, if you talk, so what I did is I took this as the definition of classical correlations. It's a direct analog with classical information theory. And now, so it's interesting, if you define correlations in this way, you will get something that cannot exceed 1 bit, if you like. I'm talking about qubits all the time now. But of course it applies to any dimensionality. But if you look at this kind of generalization of mutual information, you can suddenly get 2 bits. And here is the difference somehow you can take as some kind of measure of quantumness. And in fact, that's exactly what Zurek went on to do, and he would say, well, there is a quantum part of the correlations, which would be equal to the mutual information in this rho AB minus the classical correlations in rho AB. He didn't quite call them like that, but basically that's the summary of this. And so why is this now an interesting fact? Well, why this is interesting is because this is not just equal to the amount of entanglement, and that's the surprise. So if you ask yourself, if I subtract all the classical correlations from the total correlations, what am I actually left with? And the interesting thing is that you're left with something that's more than entanglement. And that was the surprise in that paper. So states like these, they could actually exceed the amount of classical correlations, even though they have no entanglement whatsoever. And that's exactly the same logic. So this is what was plotted in the paper by Carlton Caves and others, which then showed that somehow this quantity seems to be responsible for the speed up in these systems. So that's, again, it's a story that you can repeat in many different ways. But the point of the whole thing is that somehow, if I write it now in a slightly different way, it seems that we should not just be decomposing mutual information into entanglement and classical correlations, but there is this extra bit that we have even when we don't have entanglement. And so this is where the quantity called discord enters. So somehow you've got entanglement, you've got something that's not entangled, but it's neither classical in that sense of the word, and then classical correlation. So this is something that people have started to investigate. Can you actually decompose it like that? And I want to tell a little bit about that. I guess I've got maybe 2 minutes just to do that. So the summary is we seem to have stumbled across a type of correlation that's really genuinely due to just superpositions. The fact that quantum states are not distinguishable, even when you have different quantum states, and therefore somehow it seems that a certain extra degree of power lies in this kind of stuff. So let me just say what kind of stuff we're trying to do now, because I think if you follow this logic for two subsystems, one thing I said is that you can actually in principle extend this to any number of subsystems. But here you've got a big problem, because when you talk about the mutual information, it becomes a little bit controversial how you should define this for three or more subsystems. And I think quite a lot of you will even know that there is no unique answer probably to this question in some sense. So, you could follow the same logic as there and say, why not do S of A, S of B, S of C, subtract AB, AC and BC, and maybe add ABC. I'm kind of doing a Venn diagram picture of correlations, and I'm saying here is the mutual information, so let me add them all up, let me subtract the guys and so on to capture this area in the center. But actually, you discover to your great distress that this can in fact be a negative quantity. And of course, if you talk about correlations, it doesn't make sense. Well, I guess you could make them negative if you define it properly, but in the usual sense of this word, you shouldn't be doing that. So it's not clear how to extend this kind of logic into more subsystems. And here is why we actually went along now with another existing idea how to quantify correlations, which is simply to look at some kind of distances. So if you think of your set of states as some kind of convex set like that, and as usual, people draw some kind of picture here, and they say here are these states that are called separable states. So these would be the states that you can describe as a convex sum of product states. Then one way of thinking about entanglement of a given state here is really to look at the distance between this state and the set of all separable states. So the question you're asking is, out of all the possible states of this type, which one is the best approximation for my entangled state? And how close you can approximate tells you about the amount of entanglement in this state. So this simply here would be the amount of entanglement of A. I'm deliberately not giving any quantities here, because when I say a distance, there is an infinite choice of how you want to measure this distance, and it really makes no difference. I like entropic quantities because they have beautiful connection with thermodynamics, but you can choose whatever you like. It can be as artificial as you like it to be. So now, why not apply the same idea? Look at the distance between your state and this kind of state. That would be your entanglement. But then look at the distance between a separable state and a classically correlated state, and why not call this your discord? So somewhere here, I actually now genuinely don't know how to draw it, not that I know how to draw this either, but somewhere here is a set of your classically correlated states without any discord. And what I'm doing is looking for the closest point to approximate maybe a given separable state. And in this sense, I'm getting some kind of discord measure of my state. Okay? I deliberately drew it like a concave set, because that's one of those problems with these guys, is that they you cannot mix them together to get another classically correlated state. And in fact, the state that I just erased, what I gave here, was exactly one of those counterexamples that mixing two states of this type, which are not correlated, in fact, gives you something that's not classically correlated. So it's not a convex set, and then all sorts of techniques that we know how to find this guy fail when we talk about this measure. And then at the end of the whole thing, you've got some kind of product state here, rho A tensor rho B, and your distance to the product state would be some kind of classical correlations. So the question is, can we exploit this kind of picture? Is it additive and so on? And I can tell you that at the moment we don't really have any additive way of doing these things. So already taking a very simple class of states, which are the bell diagonal states, you can analyze these guys, you can compute them fully. And interestingly enough, your mutual information, actually you can see how this also can be generalized to more subsystems, because once you talk about distances, you can actually talk about any dimensionality of these guys. You're not confined to two subsystems anymore. But somehow, interestingly enough, this mutual information is still larger than or equal to the sum of these three quantities. So we have an example with the Bell diagonal states, where so basically just by mixing four maximally entangled states and so on, you can in fact compute all of these quantities, and you can show that they don't add up if you take certain measures of correlations. And interestingly enough, there are special cases where, for example, if entanglement is missing, then the other two remaining quantities do still add up, and things like that. So one thing we can say for sure, and that's probably the last statement that I want to really make, is the following. If you talk about pure states, and this I think is always an exception, then according to this logic, and I don't know if you buy it or not buy it, but basically entanglement in a pure state is the same, is exactly Lindblad's logic as the classical correlations. And in fact, this chord, again from this logic, is fully equal to 0. And the mutual information does become equal to entanglement plus classical correlation. So additivity in some sense is only really recovered in the pure state case. So let me give you an example. If you had a state like this, then the closest separable state would simply, I'm assuming these numbers are real, would simply be deleting the off-diagonal elements in this basis. So it would just be a mixture of 0, 0, and 1, 1. But this is also a classically correlated state by this logic. So you go straight from an entangled state directly to a state that's already classically correlated. You don't have the intermediate stage. And then if you look at reductions, they happen to be states of this type, if you like. And then you can calculate just by inspection that the mutual information, which is the distance between these guys here, is simply equal to this entanglement plus classical correlations. So all of these guys work out nicely for pure states. But as soon as you step into mixed states and say, what if I have another state in addition to this, I think you are facing an issue of this type. Okay, I think this more or less summarizes what people are discussing. It's a very rapidly evolving field. I'm sitting now, you're filming me, I should probably not say this, I'll be as vague as I can. I'm referring 2 papers now, which was sent to me in the same week, last week, by 2 top journals that we have in physics. I think you can kind of infer what they are. Okay? They are not Physical Review A. Okay, there I go, I insulted my friend, the editor of Physical Review A. Okay, so it's a very hot field. It was very interesting because when I thought about these things, it was almost 10 years ago. I think if you go back to the initial papers, and then I remember at some stage in 2004 or 5, a student of mine went to a meeting, then came back to me and said, you wouldn't believe how hot this whole field is becoming. Because I think for 4 or 5 years, no one even noticed what was going on there. And suddenly, because of this example, I guess, of a speed up, people are getting excited about quantifying these things. So the last thing is just really an outlook, which I mentioned very briefly. But I can only summarize it, what the idea is, because I don't know what the answer to that is. It would be interesting to know. The answer, so what I said would excite a physicist actually, is if you had one of those interferometers where in the middle of the interferometer, rather than doing a full unitary transformation, all you did is introduce some kind of phase between 0 and 1. So this kind of interferometer would create a superposition between 0 and 1 here. Then it would kick in a phase between the two. And then would rotate the basis so you got something like cos phi 0 plus sine phi 1. And so what you would measure at the output is cos squared of this guy and the sine squared of that. So that would be your interference. And by measuring this a number of times, you could actually infer what the phase phi is. This is the whole of quantum mechanics now summarized in 30 seconds. There is nothing else we ever do in quantum mechanics. Okay? So the question for this kind of estimates, which are very important, is does it actually pay, rather than looking at these qubits independently and doing n independent measurements, in which case the standard deviation in your phase goes as the usual short noise limit, the Gaussian kind of standard deviation. Does it pay to have them entangled initially? And we know that it does. If you really make an entangled state like the G and Z state, then so this is product. If you make a highly entangled state, you will go as something like 1 over n. There will be a square root speed up, if you like, in the efficiency with which you can estimate your phase. And somewhere between this short noise limit and the Heisenberg limit, whatever it's called, lie maybe states which are a little bit more realistic to us, because this is very difficult to maintain for a large number of systems. You cannot really do this in practice. The question is now, if I destroy the phase between these guys, but still maintain a little bit of this quantity called discord, will I still be able to go beyond the classical, the short noise limit here? And so this to us, if you answer this question in the affirmative, you would actually have something that's hugely important to us physicists and could be very, very beneficial. But I must say I don't have a clue whether this is true or not. So this is a highly studied area of metrology, but I think it's only now that people are starting to think in terms of discord and things like that. So that's actually part of the direction that we're exploring at the moment. Thank you for your attention.